Hi! Our story so far has been a story. First of all, we considered very carefully units and conversions. And the reason that we considered units and well, okay, we're going to do topic overview, and then we'll come back and do some things. After that, then we talked about motion in one dimension, which we call kinematics. Chapter 2, motion in one dimension. Chapter 3, motion in two dimensions, in which we took a look at components for vectors in x and y directions. It seemed so hard and weird at the time, but now it's probably fairly familiar to you. Then we looked at forces and Newton's 3 laws. Having analyzed forces, we looked at the special case of circular motion. And then we started analyzing the two big quantities that we care about in physics, energy and momentum. That's it. Ta-da! The whole semester on one page. That's it.
I feel like
now, where should you as a student be? Here are the following things that I want for all of you. Number one, I want you to have some conceptual knowledge. And conceptual knowledge will come in the form of being able to visualize correctly what's going on. So, for example, if I speak of uniform circular motion, all of you should be able to draw the path of a particle that's undergoing uniform circular motion. You should be able to draw velocity and acceleration vectors for the object that's undergoing uniform circular motion, so on and so forth. Visualization. Second of all, important definitions. All of you should be able to tell me what velocity is and what speed is and why they are different. And then finally, what I call folklore, important facts. So it should be the case that all of you should be able to tell me, for example, that a force that is perpendicular to the object, to the direction of motion, does no work. Or an isolated the velocity of an isolated system, velocity of center of mass of an isolated system, remains constant. Those kinds of things. So this is the conceptual knowledge that I want you all to have. And all of it should be found in your notes, but I'm not going to assume that it's necessarily at the tip of your brain right now. And then second of all, computational knowledge. There's a standard set of equations that I have emphasized through this course, and a standard set of sort of famous problems that you should be able to work. And if you have the conceptual knowledge and you have the computational knowledge, you should be able to walk in and go, I got this. Do it. And walk out. Does that make sense in terms of an overview? Now, talk to me. Which are the topics that you want to hit the most? We will hit all of them, but I want to know where to spend time. Yeah.
I think circular motion and the part of energy where it deals about work.
Okay.
I second.
Okay. Good. the
September.
stuff from the first quarter.
Yeah,
All of this.
that's forever.
We're gonna cover all of them, we should probably do it in order.
Oh, we will, yeah, we will absolutely do it in order. I just wanted to know what you feel
Just
nervous
cover
about.
everything.
Okay, any other requests? Anything that you know is confusing to you?
Are we going to have like classroom like we'll combine different area or?
Oh, yeah, absolutely. Yeah. Here, swim. Okay, let's do it.
Less. It's more peaceful. Actually, drowning is probably very technical.
Our slogan with units and conversions was let your units be your guide. And what this means is that if your equation ends up with the right units, it's probably the right equation within a constant factor. And in particular, what we learned in this chapter is that we need to put in those units with our computations. So if I ask you what's the energy of blah, 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 and your answer is 6,
That's right.
that's meaningless, and therefore not correct.
I looked through the notes and it's not supposed to. Are you sure he's?
You never heard me say let your units be your guide?
Are you okay? What? Well, you did, but not like in the notes, like house right now. Just saying.
Okay. Do you need an invitation? Here, put this in your notes. Let me write it for you.
No.
Okay, all
I'm
right.
just.
All right. A little common sense here. Let your units be your guide. Second of all, an important thing about this is that we ended up with some folklore, some conversion factors that you need to know as a matter of cultural reference. 1 inch equals 2.54 centimeters. That's a great way to convert back and forth between metric and English. And our two famous 2.2s. On Earth, 1 kilogram weighs 2.2 pounds. How come I don't say that they are equal to each other? They're not exactly equal. What does a kilogram measure?
Measures mass.
Mass, that's right. And what do pounds measure?
Force of gravity.
Force, that's right, force of gravity. So because they're not exactly equal, I don't say that they are equal, but I can use that as a conversion factor as long as I'm on planet Earth. If I go to Mars, 1 kilogram weighs something else. And 1 meter per second is the same as 2.2 miles per hour. So these three conversion factors are a good cultural point of reference. What other miscellaneous facts did we pick up? About how many seconds are in a year?
It's 30. Well, there's 3,600 an hour. It's 30. And then you have to
A lot.
multiply that by.
I'd just say it's a lot.
Times 5,600. Wait, hold on, I can do it.
1 year is about pi times 10 to the 7 seconds.
Never heard of it.
Yeah. Because it's easy to remember. I could give you a bunch of digits, but it wouldn't help. Okay. So why do you want to know these cultural reference things? Because what this means is out in the wild, you will actually have some frame of reference in order to understand what's being said to you, right? And there it is. And that was really kind of it as far as our knowledge of units and conversions needs to go. We did a little bit with density, mass, and volume, but we didn't do a whole lot with it. The key was that density is a conversion factor that converts volume into mass or mass into volume. And there it is. All of you learned how to set up conversion factors. Boy, that seems forever ago. And some of you had to learn to line up your bits and things like that. But all of you are pros at that at this point. I think.
2017.
Kinetics. Okay. Whether we're operating in one dimension or two dimension, we keep the same equations of motion with constant acceleration. But first, we had to define some terms. Velocity, rate of change of position, and therefore we define the velocity on average to be change in position over change in time. The velocity gets a vector hat. Why? It's a vector quantity. What two things does it have? Position. Did we use S or X?
X.
Oh, we used X. Okay, that's fine.
What is this?
I get confused because the AP Physics book uses R for position, and your calculus book this year or next year will use S for position,
Yeah.
and a lot of cool physics books use X. So,
What's the cool physics?
what does it mean average? The average velocity is going to be over the entire trip, whereas the instantaneous velocity is going to be the limit of that quantity. Visualize, what does this look like? If I'm working in one dimension and I have a graph of position versus time, maybe my graph looks like this, then the average velocity for the entire trip looks like a slope. And that slope, according to what you learned all the way back in Algebra 1, is change in x over change in time, rise over run, and therefore it is equal to the average velocity. So we want to visualize the average velocity as the slope over the entire trip. Yes?
Would you write that as V instantaneous, velocity instantaneous, or would it
V without a subscript is understood to be instantaneous.
Okay.
Yep. And of course, in calculus terms, you would say, oh, hey, look, that's dx dt. Yep. Meanwhile, the instantaneous velocity is going to be the slope at an instant in time. So we can, if we pick an instant in time, we can draw a line tangent to the graph at that instant in time, and our slope here is equal to v. Why is that equal to this? Because what I am doing is taking the size of my trip here, and I'm now shrinking that the size of the trip down there to one instant in time. So the visualization is that the average velocity in blue is the slope of the, over the entire trip, and the instantaneous velocity in green is going to be the slope at a given instant in time, the slope of a tangent line. Can you give me can you come up with an example of motion for which the average velocity is 0, but the instantaneous velocity is never 0?
Say it one more time.
Can you give me an example of a trip for which the average velocity is 0, but an instantaneous velocity is never 0? Okay, let's see if that works. I'm going to go forward, and then I'm going to go backward to the same spot. Is my average velocity 0?
Yes.
Yes, it is, because delta x was 0. Was my instantaneous velocity ever 0?
No.
Yes.
Yes, at one point. Right when I turned around, I had to go through 0. So you came really close. Yep.
Running around the track.
There we go. If I go around the track at a constant speed, then my average velocity is 0 for one circle, but my instantaneous velocity is never 0. So that's a tricky question. It had to be in 2 dimensions to work out. Okay? acceleration, the rate of change of the velocity. We can also talk about average acceleration, but we don't use it too much. Mostly we're concerned with instantaneous acceleration, and the reason for that is that forces give us accelerations.
Something.
Okay. Visualizing acceleration on a position graph is harder because it is not obviously the slope of anything on the position graph here. However, I can observe that for the times between here and here, my velocity is getting more negative. Can everybody see that? And so I have a negative acceleration. And for times between here and here, my velocity is getting less negative, and therefore I have a positive acceleration. Yes?
What does that say at the end after?
Oh, the limit is delta t goes to 0, delta v over delta t.
Delta V.
Okay. But if I am looking at a velocity graph, my situation is a lot simpler. If I look at a graph of velocity versus time, maybe my graph looks like this. Then I can find the acceleration at any time, again, with a slope here. Why does this slope mean acceleration? Because the slope is the rate of change of the velocity. And why does this slope mean velocity? Because the slope is the rate of change of the position. So a slope is always computing a rate of change. The rate of change of what? The rate of change of whatever the vertical variable is. Does that make sense to everybody? We could take all of what we just talked about here and put it into the general kinematics bucket. And when you do AP Physics, then we're going to do a whole lot more with the general kinematics bucket. But we focused most of our attention on a special case, an analysis model of constant acceleration. That was our favorite kind of motion to analyze. And when we had motion with constant acceleration, what we found was that our position and velocity obeyed 4 equations of motion with constant acceleration. And those equations of motion were v equals v0 plus at. Delta x equals v0t plus 1/2 at squared. Delta x also equals v plus v0 over 2 times time. And finally, v squared equals v0 squared plus 2a delta x. And at the time, those equations seemed really intimidating to us, but now we've used them so many times that they're probably old familiar friends. Doesn't that warm your heart to see those equations? But notice that the condition for using these equations is that I must have constant acceleration. If that condition is not met, these equations are not valid. So you do need to check to make sure. Wow. What are you thinking? Check for constant acceleration first before you go using those equations. How are we doing so far? Good. Can you give me an example of a situation that is constant acceleration? Free fall was our most famous constant acceleration case. And first of all, definition. Free fall means that the only force acting on the object is the force of gravity. Does that ever happen? No, that never happens in reality, because objects on Earth that are falling are always experiencing what other force? Air resistance. And even objects like on the moon or whatever are going to be experiencing gravitational forces from outside objects like the sun or the Earth or so on and so forth. But, although free fall never technically happens, there are plenty of situations in which free fall is a great approximation because those other forces are negligible. So free fall is an appropriate model when gravity is the only significant force acting on the object. And that will occur when the object has small surface area compared to its mass. Okay. And in the case where the only force acting is the force of gravity, then we say that the acceleration due to gravity is negative g, if we're working in one dimension. If we're working in two dimensions, then we would say that the acceleration due to gravity is going to be 0, negative g. And both of these say the same thing. Gravity always pulls
Straight down.
There we go. That's it. Now, in particular, when we started working problems with free fall, we called an object that is experiencing free fall. Here's the path of such an object. What do we call an object? A projectile. That's right. Projectile motion is free fall motion. And just to make sure that we're visualizing it correctly, when does projectile motion or free fall motion start?
As soon as the ball leaves your hand.
As soon as the ball or the object leaves your hand. That's exactly right. As soon as the object is launched. And when it is launched, it has an initial velocity, v0. Here's my initial velocity, v0. And the v0 determines the motion uniquely. As soon as the object leaves the hand, it has an initial velocity that will determine the entire arc. So one thing that we had to learn was that once the object leaves the hand, there are no more forces acting on it. There is no force from the hand acting on the object because the hand is no longer in contact with the object. And the way that we handled it was to split our motion up into x and y components. And to do that, we needed to take our initial velocity and we needed to put it into components. So let's take a minute now to talk about how components for any vector work. If I have a general vector A, I can resolve that vector into two components, ax and ay. And if I express that vector A in terms of magnitude and angle, then its components are going to be ax is equal to a times a times theta? Really?
No.
Yeah. Ax is equal to a times
AY over, no, it's A over.
that is true. But I'm asking a different question. What is ax equal to? From the Pythagorean theorem, we get that. Ax equals what?
A minus.
No. It should be equal to a times cosine of theta.
Oh.
Whoa, this is an interesting thing. I thought you guys were going to answer immediately. You've been doing these components a whole while.
I haven't heard the question asked like that before. I mean, that makes sense. Like, I always took it as
It may be.
cosine theta and a sine theta. I didn't really know what the exact
Oh.
I didn't really know the why about it.
Oh. Well, okay. Well, let's take a minute and to put our projectile motion on hold and make sure that we're good with vectors, because we need to be able to do that. So here is my vector in 2 dimensions, and it has x and y components to it, ax and ay. And all of you should be able to visualize those x and y components by doing an x component that is in the x direction and a y component in the y direction. This is a different vector b, like so. Then I will visualize those components by doing a bx and a by, like this. We have surely done that. Yes. And now, if we consider the angle as measured from due east, then that angle as measured from due east is called the direction of the vector, and the magnitude or length of that vector is called magnitude. And so I can write in polar form that angle as a at an angle of theta. That is one specification for the vector: magnitude and direction. The second way that I could write that is in terms of its 2 components, rectangular form. And that would be ax and ay, like so. And the key to relating those two is to observe the right triangle right here. As Delina pointed out, I can get a from ax and ay with the Pythagorean theorem. So conversion, if I need to go from rectangular to polar, then I can say that a is equal to the square root of ax squared plus ay squared. And if I need to get the direction angle, then I can observe that ay over ax is tangent of theta. This equation got a little bit complicated when our vectors were in quadrants 2 and 3, because the calculator would give us one angle that we had to understand was 180 degrees opposite from the true angle. So that when we compute theta equals inverse tangent of ay over ax, then we had to remember to arbitrarily add 180 degrees if the x component was negative. Now, Chris, you mentioned that you knew this, but you didn't know the whys and wherefores.
Yeah, just like the whole, so and so sine theta and so cosine theta. I never understood like why the vertical is you're multiplying by cosine theta and the horizontal is multiplying by
Cosine.
Yeah.
Right.
But
So let's take a look at the right triangle to get that explanation here. So first of all, can you see why ay over ax must be tangent theta?
yeah.
Yep. Okay. Now let's do the same logic here for ax by itself. If I need to get from polar into rectangular form, so what I am given is a theta, and I need to get that into x and y components. Then observe that if we divide ax by a, what do I get? The cosine of the angle between.
Okay.
So that ax over a is equal to cosine of theta. So ax, therefore, is a cosine theta. And by using similar reasoning, ay is a times sine theta. Now, Chris just illustrated for us the perils of memorizing without understanding. You see what happens? When you memorize without understanding, that's short-term gain. You can do it for the test. But then, month rolls by, 2 months roll by, and you don't remember it, or you don't know when to use it. Does that make sense? So somebody asks you a question out of the blue, and it doesn't occur to you, oh, that's what's being asked. And that's what happens when you memorize without understanding. So you want to make sure that all of you want to make sure that you understand why the rectangular to polar and polar to rectangular work the way they do. And if you have a question, now is the acceptable time to ask.
Can you do like that?
Sure. Absolutely.
Like this.
A boat travels with velocity 5 at an angle of 85 degrees miles per hour. How far east will it go? In 2 hours. So we do a little bit of visualization here to see what is being asked of us. And we begin by visualizing the velocity vector. And everybody do that on your papers. Go ahead and visualize that velocity vector. And you should have fairly quickly visualized that as a velocity with a magnitude of 5 and a bearing of 85 degrees, which is going to be pretty close to vertical. And now what is being asked of us? What is being asked of us is how far east it will go in 2 hours. So as we travel in this direction, in 2 hours, we will go a certain amount east. And here the 2 hours refers to the time, not the actual amount, not the actual distance traveled. Well, a certain amount east is another name for what component? The x component. So I'm looking for the x component of the motion. That suggests that I want to take this guy right here that is in polar form and put him into rectangular form so that I can work with it. So everybody see the logic in that? So we need to be alert to, one of the things that we needed to be alert to was when we needed to convert forms. And the answer is, I need to convert forms whenever I need some information that that form provides. Magnitude, direction, x component, y component. And so I take my velocity, which is 5 at an angle of 85 degrees, and I write it in rectangular form. Go ahead and do that. Convert. Should I get a large or small component in the expression? Yep. So if I were to guess at it just by looking at it, I would guess that the y component is pretty close to 5, and that the x component is going to be less than 1. Make sure your calculator is in degree mode, especially if you're in calculus. And what do you get for your x and y components? 4.8, and what is the y component? 4.98.
I got 0.44.
0.44. Okay, I probably just read it wrong.
Which equation do you use to get these components? Okay.
What equations were you trying to use?
I don't know, I just got really confused with all the information.
Ah, so great. How much information do you need? Since we're working in 2 dimensions, you need 2 pieces of information to specify something.
Well, I have the 5. Oh.
Yeah, the direction. That's right. Anybody else have questions on how we got our velocity here? Okay, and now because the boat is moving, yep,
Well, just a quick question. Does the time have anything to do with the problem?
yes, because we're not done yet. We haven't answered the question. We took our velocity and converted it into rectangular form, but that doesn't mean that we've told them yet how far east it will go in 2 hours. And so now because we are looking for the x direction, how far east it will go, we say delta x is equal to v0t plus 1/2 at squared, the equation of motion. And our initial velocity is 0.44 in the x direction. The time is 2 hours. And our acceleration is 0 because the boat is moving with constant velocity. And therefore we conclude that in 2 hours the boat will have gone 0.88 miles to the east and almost 10 miles north, but they didn't ask about that.
You're only using x components because we're just working on this, right?
Because I'm answering the question that was asked of me. Yep. That's exactly right. So that would be an example where we were able to convert polar into rectangular using the equations, and we knew to do that because we were looking for how far east, which is an x question. Yes?
So when you have constant acceleration, that means it's
In this case, we had 0 acceleration because we had constant velocity. Yep. Yep. Good. You're going to get a review packet for tonight, and that review packet will have you walking through more problems such as this one. There was one particular case where we needed the magnitude a whole lot, and that is when we're looking for speed, because the magnitude of the velocity vector is the speed of the object right there. And so if I have a velocity vector given to me in 2 directions, in 2 dimensions, then my speed is going to be the magnitude of that vector, just like I would compute any other magnitude. Any other questions on that? Well, in addition to the projectile motion, which was one of our models of motion that we considered, we also looked at circular motion. And circular motion occurs when the object is moving along a circular path. Because it is moving along a circular path, that means that the distance of the object to the center is always the same. Because the object is moving along a circular path, the distance from the object to the center is always the same. But that does not mean that the position is always the same. It means that the object is moving in such a way that its position is continually changing. There's its position. And the magnitude of the position vector will be equal to the radius of the circle R. When an object is moving along a circle or any other path, the velocity vector will be tangent to the motion. And the most common type of circular motion that we looked at is where the speed of the object, its velocity, is constant, and we call that uniform circular motion. And the characteristic of uniform circular motion that we discovered as we played with it and pushed Mac around and stuff like that, was that in order for an object to move in uniform circular motion, the acceleration has to point in which direction? No, straight
Oh,
towards
yeah.
the center. And what Latin word did we use to describe the centripetal? That's right. And the significance of that centripetal acceleration is that it does not change the speed of the object. Because it is pointing perpendicular to the direction of motion, it does no work, and so it does not change the kinetic energy. It does not change the speed of the object. But it does change the direction of the velocity vector. So in uniform circular motion, the speed remains the same at all times, but the velocity is constantly changing because it is changing in direction. And furthermore, we discovered that the acceleration had to have a special value in order for the object to go in uniform circular motion, and that special value was d squared over r. If the velocity, if the speed is not constant, then the object might slow up or slow down or speed up. And if the velocity is not constant, there I go again. If the speed is not constant, then the acceleration vector will point in a direction either forwards or backwards. If the acceleration vector points forwards, that is towards the direction of motion, then the object will be speeding up. And if the acceleration vector is pointing backwards, then the object will be slowing down. And what we did was to take our acceleration vector and break it up into two components, centripetal and tangential. And the centripetal component had a value of d squared over r. The tangential component was the rate at which my speed was changing.
Did we do this in class? Tangential doesn't sound familiar at all.
Did we not?
I don't think we did this at all.
Do I have you confused with physics?
I don't know.
Okay,
I
I'll tell you
don't
what
think
then.
we did that.
fair enough. The most important thing that I want you to know is the uniform circular motion, so we're just going to do that.
Everyone looked confused.
Fair enough. We'll kill it. Sorry about that.
No, that's fine.
I don't really know what
I'm not ready for
blend
calculus.
coffee
I know, I think he did.
Okay, that's good. I thought I had mentioned it to you.
I think he did. If it is, I don't know what calculus is, but it's calculus.
This is the main thing here. So that's motion. Tonight's packet, you're going to be doing a lot of motion stuff. Tomorrow, we're going to review forces, work energy, and impulse and momentum. And that's it.
Yeah,
The packet on it.
I want to go with the material.
You
That's the
didn't
most
get it.
confusing part.
Okay.